Okay, today I want to work through natural causes of climate change. All right, so we're aware that climate has been changing for a long time, and we know that it's ever since the formation of the atmosphere, the climate has been something that has changed a fair bit. So climate has changed or has been changing since the atmosphere was first formed. Okay. So let's think about how do we know about these changes. And one of the ways that we know about any climate change is through proxy data. We know because of proxy. So proxy data is inferred data. Information that we get from other sources. Types of inferred data are palynology. That's the study of pollen grains. In sediments, sometimes we find it in peat, and sometimes we can find it in rock or evidence of fine-grained fossils. Another form, dendrochronology. And this is the study of tree rings. Now, obviously, in one of our other lessons, we've talked about thickness of tree rings. If it's quite thick, then clearly it's been an abundant year or a wet year. If it's thinner, then it's obviously drier. Other features like geological, we're thinking about cross-bedding, or even planar bedding, or even ripple bedding. It's going to tell us if there was an ocean there at that time. You might notice by looking at glacial evidence. And when we think of glacial evidence, we think of moraines or U-shaped valleys. Or striations. Other evidence would be ice cores from ice caps. Now they'll tell us a lot. They'll actually tell us the composition of the atmosphere. And we'll do that by looking at gas within pockets. By looking at the oxygen 16 to oxygen 18 ratio, we can tell if the abundance of O18 in a glacier that means more has been held. This is something we looked at in one of our previous lessons. If we see an increased oxygen 16 to oxygen 18 ratio within the oceans, then we know that more oxygen 18 has been evaporated up into the atmosphere and then precipitated out as snow. Other evidence is fossil evidence. So we're thinking of corals, and that might indicate tropical conditions. We might think about swamps, or even desert features. All right, so this is our proxy data. I would expect that you would be able to know, well, most of those off by heart and give some sort of indication that you understand how each bit of evidence, each bit of prehistoric evidence lets us know whether any climate change has taken place. Okay, so let's move on to natural causes of climate change. So we're going to get down to it. Our natural causes of climate change. I'm going to have a new sheet of paper. Okay, so our causes. We're going to start off with a very obvious one, and that is our volcanic emission. So, volcanic emissions do a couple of things. The most obvious thing they do is they emit a great deal of ash. Now, ash can go into two places. It can make its way up into the troposphere, where it doesn't last very long. Ash will actually cause some lightning and some storm activity, but that's all localized and it's very much weather. So it can cause weather to change locally, lightning and storms. But that is weather and it's not climate. Ash within the stratosphere is far more interesting. You see, within the stratosphere, it can do a couple of different jobs. One of the jobs that it does is the particles or the small aerosols actually scatter and absorb incoming solar radiation. Now, the important thing, once ash gets into the stratosphere, it's going to spread. The ash will spread globally and be distributed by jet streams. Okay, so the best example that we have of this is Mount Pinatubo. And that was in 1991. Over the course of about 15 months, ash and actually sulfur dioxide, which I'll talk about in a second, actually led to a climate change of -6 degrees Celsius over 15 months. Now that might not seem a lot, but it actually was enough to, that sort of change is actually enough to cause some great deal, more increased changes in those areas that receive either a lot less or a lot more heat. We will also talk about, I'll get a different pen, sulfur dioxide. Let's get a better pen. Let's get some blue. Okay. All right, sulfur dioxide, once in the atmosphere, it oxidizes. To form sulfuric acid. Now, we're not going to go through the full chemistry of that, but during that process, more insulation is absorbed and cooled. Okay, so again, Mount Pinatubo. Now we know that it cooled the Earth by 0.6 of a degree, but between 15 and 20 megatons of sulfur dioxide was produced by this massive eruption. Okay, so that's our first main cause of climatic change. Now, if we think about this over Earth's history, we obviously think about 1991. However, there have been some further evidence of major volcanic events causing some changes in the climate. The best one I can talk to you about is the Deccan traps. Now, these are in India. These were flood basalts. And they are approximately 6 to 7 kilometers thick. Huge, big, massive flood basalt eruptions. They occurred 65 million years ago. Around about the same time as a large meteor impacted Chicxulub and caused the extinction of the KT, the Cretaceous Tertiary extinction. It's actually thought that the Deccan traps was part of that extinction. You see, these flood basalts, these massive 6 to 7 kilometer thick flood basalts, and the sulfur dioxide and ash that would have been erupted at the same time could have caused much larger changes in temperature. And those changes in temperature could have been a trigger to start further cataclysmic change. I will say could, because all evidence leads to the meteorite impact. However, often these sort of extinctions, there's normally 1, 2, or possibly even 3 events that all coincide to cause that extinction. Okay, so that's volcanic emission. Let's move on to the next one. And these are going to be our Milankovitch cycles. Okay. So there are 3 cycles. Okay, so let's talk about this guy and the Milankovitch cycles. So back in the 1920s, this guy had a theory, or he had a hypothesis, that orbital variations influence climate patterns. And if you think about it, it makes sense. If you change the distance or location of the perihelion, or the point on the Earth that receives the most, or that's closest to the sun, then you're going to change the climate. The variations that he thought were the eccentricity, the axial tilt, and the precession. So let's look at all of those. So we'll start with eccentricity. Just make sure we can see. Okay, so this is all about the Earth's orbit around the sun. Generally, the Earth's orbit is fairly round. However, if the Earth's orbit changes shape, then it will contrast, it will change the different seasons that we have, and it will mean that some areas of some parts of the Earth will have longer summers or shorter winters than others. I'm just going to draw a very poor orbit here. If I can show Earth as a green spot, right, that's the sun. And this little purple dot is the Earth. There is our nice even circle around the sun, our nice even orbit. However, if we change this orbit, you can't see that very well. If we change this orbit to an elliptical orbit, then some parts of the Earth are going to receive a lot more heat than the others. All right. So current round or circular orbit. However, every 100,000 years, we move into an elliptical orbit. Okay, now what difference this has is it changes, I guess, the lengths of the season. This changes the lengths of seasons. Okay, let's move to our next orbital change. And we're going to go to the axial tilt. Sometimes called obliquity. Okay. Currently, our axial tilt sits on a nice even 23.4 degrees. So if I was to draw Earth here, and here's our dead center. And we're going to draw in our tilt. It would look something like this, giving us 23 degrees here and 23 degrees here, or 23.4 degrees. All right, so our axis is actually slowly decreasing. So our axis is slowly moving inwards. And it will continue moving in until it gets to a point of 22.1 degrees. So instead of our planet spinning around on that axis, it will spin around on a much shallower axis. What this does is it actually increases the amount of solar radiation that hits the northern hemisphere during summer, but it also decreases it during winter. So axial tilt, changes, and every 41,000 year cycle, currently becoming shallow. As it becomes shallow, the northern hemisphere will have warmer summers, but receive less insulation during winter. So giving us greater extremes in temperature. That, again, is going to change the location on the Earth that receives the most insulation. Okay, let's talk about the last Milankovitch cycle, and that's the precession. So here, the North Pole changes. So the North Pole changes where it points to the sky. Let me try and explain this another way. It's actually a trend in the direction of the Earth's rotation. It's a trend that's relative to other stars. So every 25,000 years, the North Pole rotates. So if I try and draw this as we would see it, here's our pole. And if we can try and imagine that this will rotate, rather than the whole axis tilting, just this northern part, just this top part will move. It's called a polar wobble. And it completes. It is like a spinning top. And it makes one circle every 26,000 years. Okay. All right. So these are our 3 orbital variations. Be careful when using these. If you're asked to talk about one orbital variation, don't call it the Milankovitch cycles, because we're looking for one of these. If they're looking for different causes of climatic change, don't name all of these and expect 3 individual marks. The orbital variations is clearly one type of climatic change. And if you were to name 4 different types of climatic change and you were to go eccentricity, axial tilt and precession, you'd be losing marks. So make sure that you count these as orbital variations, and these are your different types of orbital variations. Okay, so let's move on to different types of climatic change. So, next one is going to change, let's call it that. And let's go to solar output. So every 11 years, our sun goes through a period of increased activity. So these solar maximums, I guess these are times when there are fewer solar storms and we get much more heat coming from the sun. Now, if we think about it, the location where we get all of our energy from is the sun. So if we increase that heat, then the Earth is going to get a lot hotter. So it's one of our biggest drivers. Now, the sun is actually slowly reducing the amount of energy that it produces. Why? It's because it's slowly using up the energy that it has. It's believed that the sun probably has another 4-5 billion years of life left in it. But as it changes its life cycle and the amount of solar energy it produces, then that will have a direct impact on Earth, and it has in the past. Okay. Let's go to our next. And our next one is tectonic movement. All right. So, I guess the first thing we need to know is that the surface and the oceans heat up and release heat differently. The ocean is a store of heat. The ocean has almost a memory of heat. And if you change the location of, if you make if the entire equator was covered in ocean, then it means that obviously we're going to have a lot more heat staying within the Earth, and it's actually going to completely change the way the Earth is heated. If we when we put lots of continents across the Earth, the equator of the Earth, well, obviously we're going to have a lot of rainforests, a lot of rainfall. But again, it's going to change the distribution of heat. So oceans, actually, rather than going about that, let's say that we're going to say that this change, and when I say change, I mean plate tectonic movement. Changes how the Earth is heated. Therefore, it's going to change climate. Another example is mountain building. So you remember from tectonics, mountain building is called an orogeny. And I guess mountains change the way wind has to move, and they also can increase rainfall. So they can deflect and change global wind system. And they can also, through orographic rainfall, control the weather. And if you look at it as an example, the Himalayas are directly responsible for the monsoon system in Asia. There's a little bit of reading you might want to do there, but without the Himalayas, the Asian monsoon would not occur. And I guess you could say countries like Bangladesh and India wouldn't receive the floods that they receive, but they also wouldn't receive the water that they need for everyone to survive there. So mountain building is very, very important. It does affect the way the climate works. Okay, let's stay in this sort of frame of mind, and let's now think about the oceans. Okay. Oceans are incredibly important, and the oceans and the atmosphere are so closely linked because I guess they are two sort of fluid objects, if you want to call them that. The ocean controls the heating of the whole planet. So if you think about, remember what I said before, the oceans heat up and release heat at different rates. Oceans hold on to heat more, which means they can transport heat. Ocean currents can move water that is warm, just like the Lewin current, and take it to another place. If you change the way the ocean circulates, you're going to change the way the Earth is heated. So let's look at an example. And we're going to look at the Gulf Stream. Now the Gulf Stream is a current that runs up the coast of the USA, the east coast. And it brings warm water to Europe. Now you're probably going to want me to draw this, so I'm going to have a quick go at drawing this freehand. So if we can imagine it's Canada, it's America, come down, there's sort of Florida here, it's going to go down there. We've got Caribbean here, let's call that Cuba. Forgive me, it's not a very good picture, but there's the United States. Here's the equator down here. And then over here, we've got parts of Africa and Europe. So let's put Europe further up here. So this is Canada up here. This is USA here and Mexico. So, okay, we've got our United States, our North America. If we put in, let's try and put down Africa about here. This is sort of Horn of Africa. Come up, and that's the Bering Straits, Portugal here, and here's Ireland, here's UK, and Iceland is up here. Okay, very crude. Here's UK, here's France. So, if you can see that, my lovely drawing. So, here's the equator, and our water is going to make its way upwards this way. So remember, our water wants to move this way because the trade winds blow it this way, and then our water moves up, follow across the coast of the US, and then it moves across. This is the Gulf Stream. Now, if we think about during winter, this area here gets to about minus 10 degrees Celsius. During winter, over here, this area gets to about 5 degrees Celsius. Two areas on the same latitude, virtually the same latitude. However, there's a massive difference in the temperature. Why? Because of this Gulf Stream. The Gulf Stream brings warm water. Brings warm water and takes it over to Europe, heats the air above Europe, making it warmer. If we take that away, then this area becomes as cold as that. Now, without the Gulf Stream, if you can imagine what civilization would have been like without Europe and France and Portugal and a lot of these countries here, well, we wouldn't have civilization we do today. Why? Primarily due to the fact that we've got a warm water current that sits and warms up Northern Europe. So if we change the way the ocean heats up, if we make the ocean smaller, or we change ocean circulation just on the surface, then we're going to change the way the Earth is heated. So, let's see, I'll write down a little bit about the Gulf Stream. Gulf Stream brings warm equatorial water to Europe, heating the air above it and making Northern Europe warmer. Okay, so solar output, tectonic movement, oceans. Anything else? Yeah, there's one more. Actually, there's two more. Let's get those two quick. Okay. Let's get these final natural causes of change. And let's start by drawing a little picture. You can tell what that is. That is a meteorite impact, a high velocity impact produces dust and heat to the planet. The main problem is it's dust. It's our issue. So pulverized rock and dust enters the upper atmosphere. Increasing albedo. All right. Next, and what will be our last one for today, is probably one of the main ones, is atmospheric composition. When you think about it, atmospheric composition is what the atmosphere is made of. Okay, so I guess I'm going to sound a little bit zen now, but the atmosphere is composed of many different gases. If these gases that are cycled throughout the different spheres of the Earth remain in balance, then the Earth's climate will not change. However, if we change the composition, then it's going to have some different impacts on the atmosphere itself. Some gases can cause the Earth to trap heat. Some gases can cause the Earth to cool down. Some gases trap heat. And there we're going to think about greenhouse gases. Okay, think about carbon dioxide. We'll talk more about those a bit later on. Some gases cause cooling. What naturally changes this though? Well, we've got volcanic eruptions. They can definitely cause a great deal of change to the atmospheric composition. It could be early life. If you think about prior to the oxygen within the Earth, cyanobacteria converted carbon dioxide into oxygen. So early life completely changed our atmosphere. Eustatic change. And these are sea levels. Rock weathering. So obviously rock has a great deal of carbon within it, and as rock is eroded and weathered, carbon dioxide is released into the atmosphere. Okay, that's it today for natural causes. We'll do a next one soon. Thanks, bye.